Okay, let's now look to exercise 3. In this exercise, given the system k s plus 4 s plus 6, design an ideal derivative, okay, derivative compensator to yield 16% overshoot with a threefold reduction in settling time. First thing when you see this exercise, so let's find the open loop transfer function. The open loop transfer function here, open loop transfer function 2. So then, alright, Control System Designer app, go to the app. Alright, so these are the app. Control System Designer and Analysis. You have PID Tuner, which later on maybe in advanced architect, PID architect we can look at. Model reducer, we don't look at. Linear system analyzer, we may look at it later. Control system tuners, also I invite you to go and look at them at this point. But now we focus on, in this chapter and chapter after, we should focus on the Control System Designer app. So I click on it, open it, then I implement the G. As you know, we told you by default it is 1, everything is 1. If I double click on it, the G, I can implement it, or I choose the architect first. This is the architect. I can here put it G, not the G, yes, the G. It is open loop transfer function 2. Alright, so now I'm having my G. Always I go to preferences each time, and then I make sure I'm using this format. Okay, then I don't want to focus on body editor or controller design via body plot. This is, we'll see it later. Now focusing on the root locus itself. So let's see, once we're done with the root locus, overshoot of 16%. So let's have overshoot of 16%. I know that my pole should not be on the real axis. If they are in real axis, I'm more like critically an overdamped system, right? So like here, I'm critically damped system, and I keep increasing my gain, so the closed loop location of my pole will change. 16, so we are close to 16, but not yet. So 20, maybe 10, okay, 15 points, so maybe better. Now I double click on the C, maybe if I put 46, and let's say check 16.9, maybe it's 45. Not really need to be very accurate, it's alright. Like here 16.2, so 45 gain and give me 16.2, 45. So now look at what I put it for you. So 45. This 16% I obtained it using the CISO tool or Control System Designer app when my gain K was 45. I get that overshoot. And how much was my settling time? My settling time was 3.48. 3.48. So the new settling time now will be the old settling time over 3. Okay, let me store this design and look to the question, design an ideal derivative. So now I need to add, in addition to it, I need to add S plus ZC if you wish. Ideal derivative. That's the ideal derivative. Let's add S plus ZC. Let's find a 0. Basically, that's what we should do. Alright, so I can, for example, click on it, come here, look to the 0 and add a 0, and we know that 0 will make the system faster. Okay, so to reshape the root locus, of course, but it will make the system faster. We need to check now. For example, I added it here, so you see it changed the response of my system. That's a 0 that I can readjust the gain to obtain the 16% overshoot if I wish. Right, so now this is my S plus 2. I added it at 2 point something. You see, so I can change the location of my 0 if I wish. Well, I want to get an overshoot of 16%. So now maybe, yeah, so the peak time is here. Actually, this is the settling time, so you don't have, yeah, here is your peak time, 0 overshoot. You can readjust the gain to obtain 16% overshoot. This is 16% overshoot, for example, and the settling time of 0.9. What is my settling time? Should be 3 over 1.16. So I'm less than 1.16, which I'm satisfied my settling time. So I'm faster than what's required. Okay, so this is my settling time. So I can consider it this way then. So arbitrarily I picked a 0 and I adjust my gain in order to reach the overshoot I want, and I checked if I'm satisfied the settling time or not. Alright, so this is the new compensator, derivative and gain. Alright, S plus Z times K. Also I can store it and I can compare with design 1, and you can see the difference in between. So they have the same overshoot, but this is settle faster than the one without derivative term. So the derivative makes the system faster in this case while keeping the same overshoot. I kept the same overshoot because that's my desire by changing the gain. The gain now it is 92. Alright, yeah, that's basically about this exercise. So design the controller. So we design the controller, we find ZC and K that satisfy the 3-fold reduction in settling time. It gave me more than 3 times, and I kept my overshoot the required I need. Alright. Also you could do it differently. You could do this exercise differently. Like how to do, I double click on it, I take out the 0. Alright, and let me return it to the 44.5. Alright, so they said settling time of 1.16. That's your requirement. Settling time of 1.16. So then design, right click, design requirement, view design requirement, see settling time less than 1.16. Am I right? 1.16. So I need a settling time less than 1. Okay. This is the first design requirement. The other design requirement is, so that's the settling time less than 1.16. We found it using the CISO tool. We find the settling time, all, then you divide by 3. That's my design requirement. And the other design requirement is a 16% overshoot. So now I have an overshoot of 16%. I add it and try to find a derivative compensator to satisfy my two requirements. Keep in mind, we started from gain, only gain. We changed it, as you remember here. We start changing the gain until we achieve the overshoot we want. At this overshoot, we get the settling time. We divide it by 3 because we want our compensator, in addition to the proportional, our compensator needs to reduce the settling time by 3 while keeping the same overshoot. So then this is the settling time. The other requirement is the overshoot. So design requirement, new overshoot of how much overshoot? 16%. Okay. Then my white zone becomes this one. So my goal to add the 0. So we know that the 0 will pull the root locus toward the left. So then I add 0, of course, as they said anyway. So then I reshape my root locus toward the left, and my goal is really to have my root locus inside the white region. And more precisely, because they ask for a settling time of that value, and overshoot of that value means we basically need to be in the intersection. Alright, if they said less than and less than, then we are free to be anywhere here. Okay, it's better even. But because they said at the, then let's try to reshape to pass by the intersection. So you could add a 0 here, here, or here, anywhere. So let me add a 0 on maybe anywhere. Let me add it here. And then try to reshape it. I add it anywhere. I reshape it. I want my root locus to pass by the intersection. So if I go like this, it seems like doesn't act. So if I go to the right, seems yes, we are approaching. So see, my root locus is approaching if I'm going to the right. Okay, maybe keep going. So I'm approaching right, so keep going. Maybe this is good enough. Let me zoom. I'll zoom only on one side, which is alright. So I'm not basically exactly at the intersection. If I wish, I could keep moving more. Well, somehow it seems like we are at the intersection. Yeah, it seems like we are at the intersection. So let me restore view, and then now I move my closed loop pole to intersect with them somehow here. So those are the 3 poles I have. I can zoom again and make sure I am on. So you want it more precisely, you need to zoom and make sure you are at this point. So you can change the 0 location to make sure you are intersecting with this point. But here is one point I want to tell. Okay, what about this one? So overshoot is 13 and settling time of 1.2. Alright, settling time 1.2. I'm satisfying at 1.16 and overshoot of 16. My overshoot is less. So see, now you may ask the question why. Whatever I have here, if I'm here, I'm not really satisfied what you are seeing here in the transient response. because keep in mind all the theory that we learned are for canonical second order system. This is very important. Look at it. Settling time equal 4 over sigma, so on. Just design requirements are for a canonical second order system. But this is a third order system, higher order system, and with zero. So that's why it's not enough to do it this way. Better to tune your parameter. So this is a starting point, and from here you need to keep tuning. So maybe it's alright. So I know I'm in the yellow zone, but maybe I will satisfy my requirement if even I go this way. Okay, so 16%. 16% overshoot with 1.16, 1.18, 16%. You see somehow 16%, and then I restore my view. So it seems this is satisfy better my requirement. 16% overshoot and 1.18. Here they said 1.16, so somehow I consider them fine. I compare with design one, and you can see the difference in between. So this is the second method. I'm showing it to you, so you can do it this way. The last point I want to point it out is like the zero as zero added in this case, like kind of it's canceling or reducing the effect of one of the closed loop pole, and the remaining is the two other poles. Okay, these are the two other poles remained. Okay, so here I get 1.2, 1.2, which is 1.16. All right, so you can keep increasing a little bit, but this is my point. Like the pole and zero, they are canceling each other. Now, if you want to increase it more to get 16% and 1.6 or so, as I was doing in a while, so you see the zero and pole canceling each other. That's why you still have only the effect of this to behave as second order system. See, so they cancel each other. That's the effect of the zero you added. So then it behaves as second order system. These are the two remaining poles somehow. The effect of this pole, it is neglected. Even so, it is inside the not allowed region, not in the desired region. Those are supposed to be in the desired region, in the intersection point. Keep in mind that this is in the calculation. In reality, you need those are starting point, because the transient response for a higher order system or for in general non-canonical system, the rules doesn't apply exactly. And this everything here is obey to our rules that we studied. Settling time or overshoot, all are for step response second order system and or first order system canonical system. So our system is non-canonical higher order system with zero in the controller, so therefore you should tune a little bit from the intersection point. Keep in mind again those they cancel each other, so even so then the remaining are these two poles. That's my remark, just was last remark for this exercise.